Hey everyone, my name is Miss Hu and I am a physics teacher. In this video, we are going to be learning about electromagnetic induction. For those of you who are not familiar with the way I teach, I'm using Jamboard because I'm more of a whiteboard, chalkboard, blackboard kind of teacher. I don't really like to use presentations because I feel that when we overload presentations with visuals and text, you'll be busy looking and reading instead of listening to what the teacher is saying. So, in this lesson, the objectives are to be able to define electromagnetic induction, describe the process of electromagnetic induction, determine the direction of the induced current, and state the factors which affect the magnitude of the induced EMF or current. Now, before we get started, one of the prerequisites to understand this chapter better is to make sure that you understand how forces are induced on a current carrying conductor in a magnetic field. If you haven't learned that topic yet, I would suggest that you watch my video on that particular topic because you would need to understand that topic first before we are able to learn this topic. So, what is electromagnetic induction? Now, first of all, let us recall what we have learned about forces that are induced on a current carrying conductor in a magnetic field. So, I'm going to write it this way so that you can see the relationship over here. So, I'm going to simplify it like this. Now, if we have magnetic fields from permanent magnets and we place a current carrying conductor in that magnetic field, I'm just going to put current over here. And what happens is the combination of these two will induce force. So I'm going to put it as induced force because this is the product of these two combined. So I'm going to put it like this. So combination of these two produce induced force. For electromagnetic induction, it is kind of like the opposite to this. We still have magnetic fields from the permanent magnet, but this time we will apply a force. So it won't be induced force. Let me just remove this. It will be applied force, and the combination of these two will produce induced current. So that's electromagnetic induction, in an overview. So if we look at the definition of electromagnetic induction, it is the production of an electromotive force across an electrical conductor in a changing magnetic field. Ooh, so long. What does this mean? So if you recall, electromotive force is actually the total voltage of a power supply. So in this case, if you're wondering where's the power supply, well, we are now going to make the power supply. That means the process of what we're learning of electromagnetic induction, whatever happens here, we're inducing a voltage. So which means that because it becomes a power supply, it is now the source of voltage and current. It is not a power supply. Hence, that voltage provided is the electromotive force. That's why we have the term electromotive force in this particular definition. So the electromotive force is produced across an electrical conductor, for example, the wires, in a changing magnetic field, which means that as the magnetic flux changes across the electrical conductor, then electromotive force will be produced and therefore current will be produced. Let's see an example in this case. So I know this is a very simple diagram. So I'm going to label here. Let's make this the south pole and let's make this the north pole. And the blue lines here are the magnetic fields between these two permanent magnets. So I'm just going to draw the arrows here to show that these are the direction of the magnetic field. Now imagine we have a conductor. So for the purpose of this explanation, I'm just going to draw a rectangle here. Let's imagine that this is a metal wire and we're going to move it across the permanent magnet. Now imagine that we just leave the wire in there. Do you think anything's going to happen? Obviously not, right? It's not like magic where you put something that doesn't move and whoo, suddenly something appears. No, there has to be action in order to produce something. So what happens here, in order to be able to induce current, we need to move the wires. So when we move the wires, we have to think of it as cutting the magnetic field. So which means that the magnetic fields are moving from right to left. The wire needs to cut across. So if these are the magnetic fields, for example, then it's the wires, they've got to cut across. You cannot have them move parallel. Parallel will not induce any current. If you're wondering, what about cutting it at a different angle? And actually, it's possible. You can if you move it at angles other than 90 degrees. But the best is to move it across at 90 degrees. You just need to remember that because we're producing current, which is electrical energy, in order for us to generate electrical energy, there must be kinetic energy in order to convert this to, electrical energy. In terms of the angles which we cut the wire at, so I'm just going to draw a 2D diagram here. Let's just draw the magnetic fields in this case. In order to induce the highest value of current, it really does depend on the direction of motion with regards to the magnetic fields. So if I were to draw this, let's say this circle represents the cross section of the wire if we were observing it from this point. That means, let's say if our eyeball was here, this is the cross section of this wire. In order for maximum current, the best would be to move this wire perpendicular across 90 degrees to the magnetic fields. If we move parallel, then it will be zero. If we move it at an angle, then we can generate current, but it won't be as much. So just to help you visualize this, if this is the direction of movement, this way, 90 degrees, this would produce the maximum. Whether it's going up or down, it doesn't matter as long as it's perpendicular to the magnetic fields. If we are moving the wire parallel, it would be zero or minimum. Any direction that is at an angle can produce some current, but it depends on the angle. The larger the angle between the magnetic field and this direction of motion, then of course the greater the induced current would be. That's why at 90 degrees it is the maximum. So this is of course all related to Fleming's right-hand rule. Now we did learn about Fleming's left-hand rule in the topic of forces across a current-carrying conductor in a magnetic field. And this is very, very closely related. So like I said earlier, over here on slide number 2, the combination of these two produce induced force, whereas the combination of these two produce induced current. So what I always tell my students to help them remember this more easily is to remember that when it comes to induced force, they need to use Fleming's left-hand rule. And when it comes to the production of induced current, they need to use Fleming's right-hand rule. So I'm just going to copy and paste here so that I don't have to retype the whole thing. So let's compare Fleming's left-hand rule and Fleming's right-hand rule side by side. So if you recall, Fleming's left-hand rule, we need to use our hand this way. So remember, gun and trigger finger. So you've got the thumb, index finger, middle finger. So let's look at the diagram over here. So the thumb represents the force. Your index finger represents the magnetic field, and your middle finger represents the current. If you watched my earlier video, the mnemonic I came up with was feed my cat. Now, you can use the same mnemonic for the right-hand rule. So although this diagram shows it a little bit differently, but you can still remember it as feed my cat. So that means the thumb still represents force. So let's put feed here. Okay. Although they call it motion because we're actually moving the wire, but you can also think of it as the direction of the force applied. The index finger represents the magnetic field, M, my magnetic field, and the middle finger, C, current, cat. So remember, feed my cat. So thumb, same thing, index finger, same thing, middle finger, same thing. What you do need to differentiate is when to use which rule. So remember, you use Fleming's left-hand rule when we are inducing force, and we use the Fleming's right-hand rule when we are inducing current. So if you can't remember which is which, you always just remember it this way. Fleming's left-hand rule, you use this in a circuit where there is power supply, and you use Fleming's right-hand rule when there is no power supply provided, because in this case, the electromagnetic induction is the power supply. So if we refer back to the definition of electromagnetic induction, the production of an electromotive force across an electrical conductor in a changing magnetic field. Here's the electrical conductor, and as we move it across a magnetic field, we're actually changing the magnetic flux. That's how current is induced inside the electrical conductor. Of course, in order for this to be useful current, we need to connect this wire to a complete circuit. To determine the direction of the current flow inside that wire, we need to use Fleming's right-hand rule. Now, let's look at another way to induce current. So we have in this slide here a solenoid, but the solenoid here, which is a wire coil, it is not an electromagnet because there's no power supply. Because remember, yes, we are now the power supply. We need to supply the motion here in order to produce the current that will flow inside this circuit. Now let's take this bar magnet and we move it in and out of the solenoid. So on this diagram, you can see that there are magnetic fields, and as we move it in and out of the solenoid, you can see how the wires from the solenoid are cutting across the magnetic fields. This also will induce current or electromotive force. Because when we come back to the definition of electromagnetic induction, it is the production of an electromotive force across an electrical conductor in a changing magnetic field. So the wires here are the electrical conductor, and as we move it across, there is, of course, the cutting of the wires will have a change in the magnetic flux. The key word in both situations is that the wires are cutting across the magnetic fields. Like here, the wire cuts across the magnetic field, and like here, the wires are cutting across the magnetic field. Now, in this situation, we also need to be able to determine the direction of the current flow. But if you look at this, you can't use Fleming's right-hand rule in this case. Fleming's right-hand rule, they're all right angles, but this is a solenoid. How do we use it in this case? So in this situation, we need to apply Lenz's law. Now, Lenz's law states that the induced current always flows in a direction that opposes the change of magnetic flux that causes it. What does this mean? The key word here that we need to take note of is the word oppose. And let me show you what this means. Say we have a solenoid like this. As you can see that there's no current flow. And I'm going to take a bar magnet. I'm just going to draw it really quickly. So say this bar magnet has a north pole this way and south pole this way. Now, it is important to take note of the polarity of the bar magnet as well as the direction that it's moving relative to the solenoid. So say, for example, we move the bar magnet inwards. Remember that the solenoid will oppose everything that we do. It is not your friend. So if you're going to push the bar magnet in, the solenoid will try to push it back out. How is it going to push it back out? The magnetism from the bar magnet will induce a secondary magnetism in the coil, which means that now this coil or solenoid will become an electromagnet. So in order to push the bar magnet away, it will induce its own magnetic field here by creating a polarity of north on this end in order to repel the bar magnet. So if this side is north, obviously this side would be south. If we were to reverse the direction, so I'm just going to very quickly copy and paste here. So if we were to reverse the direction of this bar magnet, let me just do this really quickly. So we have north and south, and this time we're pulling it away. Remember, it's going to oppose. So oppose doesn't always mean repel. Although in the first diagram, yes, it's repelling, but in the second diagram over here, it will oppose by trying to pull it back in. That means if you pull the bar magnet out, it will try to pull it back in. So it will form a polarity of south on this side in order to try to attract it back. And that side will be north, of course. So you can think of it as like, this solenoid is like a child or a childish person who is very fussy. Like when you give this something to this person, like, no, no, I don't want it. And then when you take it back, no, no, give it back to me. So when you push in, it will try to push it back out. And when you pull it out, it will try to pull it back in. So that's why when you push it in, it will try to repel by forming the same polarity. When you pull it back out, it will form the opposite polarity in order to try to attract it back in. For further understanding, you have to understand that for this, just to elaborate a little bit further, in the second diagram, you have to imagine it as if the bar magnet was already in, and what we do is we pull it out. Now, if we were to use a south pole instead, the same concept applies. So do not remember, the polarity of the coil, but instead remember that it's always opposing. So let's say now this side is north and this side is south, and this time we are pushing the bar magnet in this way, which means that because you're pushing the south pole in, the coil will try to repel by forming south pole here, and the north pole will be on this side. And also, if you were to pull the bar magnet out this time, that means, like I said earlier, you imagine the bar magnet was inside and now you're pulling it back out. If you're pulling the bar magnet out, it will try to pull it back in, right? So it will try to attract it back. So that means this side will now become north and this side will become south. So how do we determine the direction of the current flow then? Here's where you need to use the right-hand grip rule. So the right-hand grip rule is used this way. You've got to form your right hand into, a fist, thumbs up. Your thumb will represent north. Your fingers will represent the solenoid. So, for example, in the first diagram, if north is on the left side, point your thumb towards north, and you can use your pencil as a reference here. Grip your pencil with your fingers. So that means now your fingers are the solenoid, and observe the direction of your fingers. Now, because you've pointed your thumb to the north, you see the fingers from your point of view, they're going up, correct? Which means that the direction of the current is flowing upwards on the side of the coil closest to you. So same thing here, if north, this is where the current direction would be flowing. If north is on the other side, on the right-hand side, point your thumb to the right, again, grip your pencil, and your fingers are now pointing downwards, correct? Which means that on the side of the coil that is closest to you, current is now flowing downwards. So you can see, yes, the current direction does change, and it depends on the polarity of the bar magnet as well as the direction that it's moving relative to the solenoid. So what we've just learned are two different setups to induce electromotive force. So you can move the bar magnet in and out of the solenoid, or you can move the wire across the magnetic field of the permanent magnet. So in general, when we talk about the process of inducing current, remember this. The first step is the cutting of the magnetic fields by the conductor. Conductor. Secondly, the cutting of the magnetic fields will cause electromotive force to be induced. This would then cause induced current to flow. Let me write this way. Current is induced to flow through the conductor. So generally, it's the cutting of the magnetic field followed by induced electromotive force, then followed by induced current. So let me just draw arrows here so that you can understand this process. Next, let's take a look at the factors which affect the magnitude of the induced electromotive force. So whether it's the first setup where we move the wire across the magnetic fields of the permanent magnet, or we move the bar magnet in and out of the solenoid, they share similar factors actually. So let's think. how can we make the induced EMF or the induced current higher? So for one, definitely the speed of motion, right? So if we move the wire or the bar magnet more quickly, that would of course increase the magnitude of the induced electromotive force. So speed of motion would definitely be a factor. It's longer. Also, the strength of the magnetic field. So if you use a stronger bar magnet, obviously there would be more magnetic field lines. Strength of magnetic field. When there are more field lines, what happens is when the wire cuts across more field lines, obviously more induced EMF and more induced current. There are also other factors which would include presence of soft iron core. So for example, in the solenoid, if you place a soft iron core inside the coil, it also strengthens the magnetic field that will be induced and therefore will increase the induced EMF and current. Even for this situation, although there's no soft iron core to wrap around, but later when you learn about generators in the next video, you can actually place a soft iron core inside the coil, and that would also increase the induced EMF and induced current in the generator. Besides that, you can also, for example, for the solenoid, you can increase the number of turns. Whoops, that was not number of turns of the coil. So the more turns there are, of course, the more wire that it will be cutting across the magnetic field. So therefore, also higher induced EMF and current. Likewise, for the single wire, it doesn't work. But if you make it into a coil, like for a generator, that would also increase the induced EMF and current. And if you use a wire with a greater diameter, so diameter of the conductor also plays a role, because if it's a smaller diameter, larger diameter, there is more space for the electrons to move. So if you move these two kind of wires across the magnetic field, larger diameter, there's more space for the current to flow, right? Therefore, it also causes a higher induced EMF and induced current. So these are the factors which affect the magnitude of the induced EMF. Now, all these factors can be explained with Faraday's law. Faraday's law states that the magnitude of the induced EMF is directly proportional to the rate of cutting of magnetic flux. So if we look at all these factors can be explained with Faraday's law. So there is a formula that is related to Faraday's law, but at this level, we don't have to learn the formula. So the formula is not covered in this video. All you need to know, yes, there is a formula. That's why the relationship of directly proportional is given here based on what Faraday had discovered. So if we look at all these factors, like I said, these factors can be explained with Faraday's law. So if you're wondering, okay, but does rate, because I get this question a lot, isn't rate only for speed? No, it's for everything. Because the speed, yes, the speed does increase the rate, but so do the others. So for example, if you have a field where there's only a few lines, compared to if you have a field with a lot of lines, the rate here refers to how many magnetic flux you can cut per second. Higher rate, more flux can be cut per second. So if we move a single wire with the same speed across these two fields, because the stronger magnetic field has more lines, therefore the rate increases. Likewise, when you have a soft iron core, it strengthens the magnetic field, which also increases the magnetic flux. Number of turns of coil, same thing. More turns on the coil when you move the same speed, more wires are cutting the magnetic field lines at the same time. Diameter, also, yeah, because a larger diameter cuts more at the same time compared to a smaller diameter. So all these factors can be explained with Faraday's law. So as a summary of what we've covered in this video, we now know electromagnetic induction is a production of electromotive force due to a changing magnetic flux. It is by cutting the conductor across a magnetic field like this, or by moving the bar magnet in and out of the solenoid, that we're able to induce electromotive force and therefore induce current. In terms of determining the direction, Let me write that over here for the overview. So in order to determine the direction, if we have this kind of setup with a single wire and magnetic fields that are parallel like this, you would be using Fleming's right hand rule in order to determine the direction of the induced current. But if you're using a bar magnet in another solenoid like this, you would be determining the direction based on Lenz's law. Whereas, if we were looking at the factors which affect the magnitude of the induced current, whether it's the first setup or the second setup, both can be explained using Faraday's law. So I hope you have found this video helpful and educational in understanding a little bit better about electromagnetic induction. If you like this video, don't forget to click like. Remember to subscribe to my YouTube channel, Physics Rocks, for more video lessons just like these.